and also a writer and speaker on JavaScript, JSON, and related web technologies. The Wikipedia article is super long, so I'm not going to go all the way down, but I'm going to get to the event website. And so Douglas was born in Frostbite Falls, Minnesota, but he left when he was only 6 months old because it was just too damn cold. He's a registered voter. He turned his back on a promising career in television when he discovered computers. What shall we do? Shall we wait? Wait for 2 minutes. Okay, this will take at least 2 minutes. This will take at least 2 minutes. Okay, so we don't want anyone upstairs to miss this talk, and the team has worked very hard to get to this point. So Douglas has worked in learning systems, small business systems, office automation, games, interactive music, multimedia, location-based entertainment, social systems and programming languages. He's the inventor of Tilton, the ugliest programming language that was not specifically designed to be an ugly programming language. And he's best known for having discovered that there are good parts of JavaScript. This was the first important discovery of the 21st century. He also discovered the JSON, the world's best-loved data interchange format. Douglas's Wikipedia entry talks about Atari in the early 80s, and games that the older generation here have probably played, and many, many, many other things. All I can say is that I'm privileged to have the chance to introduce you, Douglas. Thank you very much for coming all this way. Let's thank Agile Actors for making it possible. And of course, the Voxxed Days team for putting it all together. And Douglas, the floor is yours. Thank you so much. Welcome. Big round of applause for Douglas. Numbers, here we go.
So it is great to be here in the city of the goddess of smartness with all of you smart people. So our computers today are all over the world. They're managing and mediating almost all human activity. Computers are into everything. And computers are machines that can process numbers. That is the only thing computers can do. They can add and subtract, multiply, divide. They can move a number from one place to another, and that is all that they can do. So it's amazing, almost magical, that so much is happening with computers when really what they can do is so incredibly limited. So numbers are so important in computing. I thought it'd be good to spend an hour looking at what numbers are, where they came from, and how they work. So numbers for us individually start with fingers, right? You can count on fingers. But long, long before we had counting, we were living in trees and eating fruit. And it turns out fingers are really good for doing those things. And we were very happy living that way for millions of years until the climate changed and the trees started to thin out and grasslands appeared. And we were forced to drop out of the trees, walk on the ground in order to find additional sources of food. Now it turned out having fingers was useful when it came to using tools. So the first tools were sticks that we used to dig up roots in the ground, and rocks, which we used to smash the tubers because we have monkey teeth that are designed to eat soft fruit, and we couldn't eat that other stuff. And so we had to learn how to cook, basically, in order to keep ourselves alive. And that ability with tools helped shape our next stage of evolution. So our upgrades allowed us to invent knives made out of volcanic glass and to manage fire. And eventually we figured out how to put seeds into the ground in order to force the production of food. And with agriculture, we became so successful that it completely changed the way that we organized ourselves. So we changed from clans and villages to cities and countries. And that was a really big change. And in order to manage that new level of scale, we had to get much better at dealing with numbers. because our brains are not very good at remembering numbers, and civilization requires a lot of numbers. So at first we would, after we ran out of fingers, we would make marks on a wall or make notches in a stick or knots in a cord. But eventually the needs of civilization outpaced that stuff, and we were forced to invent accounting. It's true, accounting is where this started. That's where we developed the need for writing. Because it wasn't enough to make a list of numbers, you need to have annotations with those numbers so that you could remember what the numbers represented. And so that leads to the invention of writing. We use writing to do all sorts of stuff, to make literature and laws and letters, but it started with spreadsheets. And the invention of writing is the most important thing to have happened, I think, ever to humans. It's our most important invention. And it happened 3 times in our history. The first time was in the Fertile Crescent, either in Mesopotamia or Egypt. The smart money says Mesopotamia. I think it was Egypt. Later it was also discovered in China, and it was also discovered in America. In Central America and Mexico, there was a civilization that was doing stuff with numbers and writing. Unfortunately, that civilization didn't survive the Spanish conquest. So let's look at some of the number systems that people came up with. So this is the Egyptian system. A stick means 1, a piece of rope means 100, and so on. And they have a symbol for 1,000,000, which is a guy saying, it's a lot. But the symbol doesn't mean it's a lot. It means exactly 1,000,000. That's some mathematical sophistication, right? And so the way it's an additive system, to make a number, you have a bunch of each of those things until it adds up to the thing that you're trying to do. They could do lots of other things as well. They figured out that a 3, 4, 5 triangle gives you a right angle, and they understood why right angles were really important. They had an approximation for pi. They had an amazing system for dealing with fractions. And they taught their system to some of their neighbors, including the Phoenicians. The Phoenicians were traders who sailed all around the Mediterranean and even into the Atlantic, trading with everybody on the coasts. And they took the Egyptian system and brilliantly simplified it. Instead of having the thousands of characters that are in hieroglyphics, they got it down to a couple dozen, and they taught their system to the other people they traded with, including, you may have heard of these people, the Greeks. At one time, this is a system that was used in Greece for a while. There were 27 characters in the alphabet, and they assigned the first 9 of them to the digits 1 through 9. And the next 9 get the values 1 through 90, and the next 9 get the values 100 to 900. So it's another additive system. Generally, you take 1 or 2 or 3 characters and put them together, and you can get all the numbers less than 1,000 by doing that. Rome got the Greek letters and adapted them, but their number system looks more like the Egyptian system. They've got I representing the stick for 1. X is a bundle of sticks tied together. They added an innovation to try to make the number smaller by introducing half symbols. So V was formed by taking an X and cutting off the top half. And they did similar things for the others. The other innovation was they made it not just an additive system, but also a subtractive system. If a character in front of a number is smaller than the next one, then it gets subtracted rather than added. China came up with a really elegant system. I like this one a lot. They've got characters representing 1 through 9 again, and then they have special modifiers for dealing with the places. So I've got symbols for 1 or 1,000, and then another set of symbols for dealing with bigger numbers. So if I wanted to say 40,000, for example, I'd get a 4 and a 10,000. Really elegant system. But the big breakthrough was in India. India, they come up with the 0, which is a really big deal. They also had a 0 in Central America. And it's a positional system, so that, well, you know how this, I don't have to explain what this is working, but this is really good stuff. And the nice thing about this particular system is it's been so well adopted all over the world that no matter what country you're in, what language you speak, we can all interact with these numbers. We all understand the numbers to mean the same thing. So all of these systems worked, and they all worked really well. All of these countries were major, big deal empires, so all of these worked. The first set were optimized for use with abacuses, you know, arrays of beads that you move back and forth on strings or wires. And, you know, all of these represent the same number. So you just count the number of things and move that many beads. The advantage of the Indian system was that you could add a column of numbers without using an abacus. And that's not something that you can easily do with any of the other systems. Today, is that an important thing? No, because we don't do arithmetic anymore. You know, machines do all the arithmetic, so it really doesn't matter which of these we're using. The computer will have its own representation internally. But in terms of UIs, things like the Egyptian system were really good because there was a lot of redundancy in it. Getting one character wrong was difficult to do, but the error was obviously noticeable, whereas in the Indian system, getting one number wrong, and it's a total mistake. But on the other hand, I can't imagine typing in a phone number using Roman characters. So that'd be really hard, wouldn't it? Our system seems to be optimized for UIs, although eventually that's not going to be important either. And I can't remember the last time I actually dialed a number into a phone, so that advantage may be going away. But it was a really important system, so the Indians figured it out, and they taught it to the Persians, who called them Hindu numbers, and they taught them to the Arabs, and the Arabs taught them to the Europeans, who called them Arabic numbers. But the thing took off, and they're really useful. And they're useful not just because they make certain kinds of calculation easier. I think they're actually more important for other reasons. For example, we can look at the whole numbers, and the positional notation that we're using is actually a shorthand for polynomials. This is where we are introduced to polynomials, and that turns out to be a really important thing. There's a lot of mathematics that's tied into that, and we first see it in the Indian numbers. Also, we can think of each position as being on the number line, where that place gets raised to 10 and multiplied by whatever the digit is. The Indians figured out that we could do that in both directions, and so they come up with negative numbers. Everybody had subtraction, but they didn't have negatives. And it turned, because they're hard to understand. You know, what is minus 2 loaves of bread? But it turns out that's a really useful thing. And so once you have negative numbers, then the number line can go in both directions. And now we have a really straightforward way of dealing with fractions, that we can deal with fractional positions in exactly the same way we deal with the whole positions. We just have to keep track of where the decimal point is. So the Indians used an overline to mark the ones position. And other people tried to put a line in between the ones and the fraction part, and eventually it turned into either a period or a comma. Some countries tend to use period, some people use comma, which didn't used to be a problem because the countries were all pretty much kept to themselves, and so they could do whatever they wanted and it didn't matter. But today, all of this stuff is happening on the internet. And now it's kind of a mess. And there are mistakes, sometimes very expensive mistakes, that can occur because of the confusion between the period and the comma. And we haven't moved everybody from one to the other because there hasn't been a clear argument for which is better. And in fact, there isn't such a clear argument, except that there's it's obviously true that it'd be a whole lot better if the whole world just used one of them. And so I predict eventually, and maybe not too long, the world will finally decide that it needs to be the period. And the reason they're going to decide that is because of you. That we use period because that's what our programming languages want to do. And eventually we'll teach the rest of the world that this is how it works as well. And in fact, this all goes through your software, so you've got a little bit of leverage here. So all of the systems that I showed you are base 10 systems. Now, why is it base 10? That's why. You know, if we counted the fingers, base 10, and that applies to writing. But that turns out not to be universal. For example, there were some places where they were using base 20. For example, in America, they were doing base 20 systems. So how do you get to base 20? Obviously, you count your toes. Yeah. But there were other bases too. For example, there are a number of cultures that used base 12. And how do you get to base 12? It's the 10 fingers and 2 feet. And you know, unfortunately, there's still a lot of base 12 where I live. You know, we've got 12 to a dozen. We've got the 12 hours on the clock. We've got 12 inches to the foot. That's actually Britain's fault, England's fault, that they were smart enough to move away from it. But in my country, we're still stuck with that, so we're dealing with that. The oddest base that I've seen was base 60, which was used in Sumeria. And you look at that and go, how do you get to 60? You know, how many, what can you count to get to 60? So what I think happened was, it was not by design, it was by committee. That they had two cultures that they were trying to integrate in order to build their empire. And one of the cultures used base 10, and the other used base 12. And they need to get agreement on this is how we're going to do stuff so we can reconcile our books. And the correct decision should have been, we'll pick one, and if the other guys don't go for it, we're just going to lop their heads off and we'll be done with that. But they didn't do that. Instead, they tried to make everybody equally unhappy. And so the compromise was, let's use the least common multiple, and that'll be our base. So that was a mistake that they made 5,000 years ago, approximately, and we are still stuck with it. You know, this number is still based in our navigation systems. If you've ever done geocomputing, you know that's really an unnecessary source of difficulty and error. It's in our timekeeping. It's all over the place, and I have no confidence that even you have the power to get rid of this. So we're stuck with that. But it kind of shows how a committee can make a bad decision, and 5,000 years ago, we're still dealing with the consequences of it. The most important thing, I think, about the Indian system was that if we apply the idea of changing bases, we get the binary system. And this is what makes our computers work. And this is brilliant. And the binary system would have been a difficult thing to discover in any of the other systems, but it kind of falls out of the Indian system. And that's why I think the Indian system was a big win. When you go to binary, you have to figure out where are you going to put the sign bit. Generally, you want to have a bit which is either a 0 or 1, which means either plus or minus. And you can either put it at the beginning of the number or at the end of the number. It doesn't matter, but you need some convention for how you do that. And there are three ways that are commonly used for representing sign bits. One of them is maybe the simplest one is called signed magnitude, where we simply pick one bit and we say you don't contain a value, you just contain a sign. And it's really straightforward, but there's one weirdness about it, and that is if you put a minus sign in front of a 0, you get minus a 0, which is something that shouldn't exist, but it's representable. Another system is one's complement, which is also easily done. You simply knot the number, flip every bit. If you flip every bit, then it's a negative number. The thing that's a little odd about it is that if you have an overflow, which could happen all the time, if you have an extra carry that goes outside, that carry bit has to get added back in. So you might have to do an add and an increment depending on what happens. And also you've got the weirdness, again, where you've got 0 and minus a 0. Then there's 2's complement, which is what is used in most of our systems today, where we do the end around carry at the time we do the negation, so it makes things a little bit cleaner. So there's only 1 0, which is a really good thing, but unfortunately there's an extra negative value which does not have a corresponding positive value. And that can be weird because if you try to take the absolute value of that thing, you still get the negative thing, which could be a source of errors. So my advice is that we should not have these extra values anymore. We should either take the minus 0 or the extra negative and turn that into a sentinel, which tells us this is not a number. For example, there's the index of method in Java and JavaScript and C# and a lot of other lousy languages. The type system in all those languages doesn't allow for something to tell you that the search that we tried to do failed. And so as a compromise or a workaround, they return -1 instead. Except -1 is an ordinary integer. It looks like any other integer. So if you include that in a calculation, you're going to get something that's wrong. And I think there's an opportunity that if instead these systems would return that null value, which says nothing found, this is not a number, then that cannot get rolled into an ongoing computation, and so we can catch errors much more quickly. So let's talk about types a little bit. So we have ints as the representation of integers in our modern languages. Most of our languages don't have something called int32, but most of them have an int32. You know what that means. So if you add 2 int32s together, what is the type of the result going to be? Any guesses? Anybody? No? Well, the answer is int33. int33, because if you add 2 32-bit numbers together, you can get 1 more bit of significance out of it. Unfortunately, JavaScript or Java does not have that, and so Java can easily get that wrong. Let's try another one. We're going to multiply 2 int32 together. What will be the type of that result? Any guesses? int63. int63. I would have taken int64. That's pretty close. But again, Java is totally wrong on that. Now, it turns out that CPUs understand this problem. So if you look at an Intel processor, for example, if you add 2 32-bit things together, there's an extra bit in the architecture called the carry flag, which contains that critical 33rd bit. You need that bit. And they knew it's important, so they calculate it and they put it in a place where you can find it. And when you do a multiply on the Intel machine, they give you the full 64-bit result. They also have another flag called the overflow flag, which is true when that extra stuff is really important. That if you throw that extra stuff away, you're going to cause a really tremendous error, an overflow error. Unfortunately, most of our languages discard that information and in fact make it impossible for you to obtain it. And so you can't write correct programs in these languages because you're not getting all of the information that you need. So overflow happens if you have a result that you're trying to put into a word and it doesn't fit. So what should happen in that case? So I think a good thing to do would be to store a null value or not a number value there. I think that would be the right thing to do. And we just saw that with integers, there's a way to do that. There's an extra value that we're not making good use of, which could be reserved for that function. Or we could instead store the largest possible value that does fit. This is called saturation, and it's often done in computer graphics and signal processing, but you don't ever want to do it in financial applications, right? We're agreed on that. Another thing you might want to do is fault. You know, you can throw an exception or have something happen so that you can disrupt the current flow of the program and go to an alternate flow. That might be a useful thing. Maybe the machine should halt. That's sort of an old school idea. You're not going to get to 9 nines that way, but that's better than what we do, because if what you want to do instead is to maximize the creation of errors, you want to discard the most significant bits without notification. And in fact, that's what all of our modern programming languages do, except for JavaScript. JavaScript doesn't do that, but C, C#, C++, Java, all those languages have this terrible design error in them. So let's talk about fractional arithmetic in binary. So one way to do it is with scaled arithmetic, where we'll take a value and we'll multiply it by a scale factor, and that gives us a scaled factor. And that's often used in signal processing. It was used in computers before we had floating point, before floating point was invented. And it works, and it can be really fast and convenient. Well, it's not convenient, it's actually very inconvenient. You can only add two values together if they are scaled the same. If they're not scaled the same, you have to scale them to match before you can add them. Multiplying is a little bit easier, except you have to divide out the scale factor. Otherwise, you start to accumulate that. And in division, you have to multiply in the scale factor before you do the division. So that gets a little bit more expensive. And in some applications, it may be difficult to find the optical scale value. So because of this difficulty, we invented floating point. Floating point is approximately real. It's much more convenient and accurate than scaled arithmetic. And the original form of floating point was decimal floating point. And it was implemented in subroutines and written in software, and it was very, very slow. So there was interest in moving that into hardware. But it was difficult to do because at that time, hardware was made out of vacuum tubes, and doing decimal floating point required frequent divisions by 10, which is kind of hard. So some genius had the idea of doing this is decimal floating point. This is what I was just talking about. But it was perceived as being too expensive because of the scaling by 10. And so they came up with binary floating point. First person to do binary floating point was Konrad Zuse, who was building computers in the living room of his parents' apartments in Berlin. Unfortunately, he was doing it during the Second World War, and he got bombed. But he was the first person to figure out binary floating point. A generation later, other people rediscovered his ideas, and we're still working with those conventions. So the actual scaling of the numbers or formatting of the numbers is more complicated than with the decimal stuff. They take the sign bit, or the significand, which is the thing containing the information of the number, and split it into two pieces. And they move the sign bit to one side and the rest of it to the other side. And then they take the exponent and fiddle with it so that the sign bit of the exponent is flipped. And the reason they do that is so that this number, as an integer, if you interpret it as an integer, will compare correctly for two numbers. So if you want to ask, is this number bigger than that number, you don't have to do the floating point to compare, you can do an integer compare. And that used to be a lot faster. It's not that important anymore. Unfortunately, there's a problem that comes with binary floating point, and it looks kind of like this. 0.1 plus 0.2 is not equal to 0.3. And that's a problem. I think that's a big problem, particularly if you're dealing with money, that we represent money as decimal fractions. And when you're adding up people's money, they have a reasonable expectation you're going to get the right sum. And we're not guaranteed to do that because we cannot exactly represent decimal fraction in binary floating point. So here's what's going on. If I want to represent 0.1 as a binary fraction, Well, it turns out there's not an exact representation. So I can add a 16th and a 32nd, and that gets me a 0.93. That's not quite enough, so I need to include some more bits. But I can't include enough, because it turns out decimal fractions in binary are infinitely repeating, similar to the way a third in a decimal system is infinitely repeating. So because it's repeating, and because we don't have an infinite number of bits available, the best we can do is approximate that value. So anytime in your program you have a number constant with a decimal point in it, you are introducing a little error into your program. And sometimes the errors will cancel out, but as you know, often when we have little errors, they tend to accumulate instead. So because we don't have infinite bits, depending on the type of number, whether it's a float or a double or whatever, we only have so many bits available, so we're going to have to truncate that infinite expansion. And if we truncate before a 0, then we lose all of the 1 bits that followed, and our number is going to be too small. But if we truncate in front of a 1, then we'll round up that 1, and our number will be too big. And that's just the way it is. They'll never be right. Then there's the problem, because our numbers are not exact, we lose the associative law. So the associative law holds only if all of the inputs, outputs, and intermediate results can be represented exactly. If they can't be represented exactly, and in the case of binary representations of decimal fractions, they can't, then we lose associativity, which means that the order in which you add things can change the result, which is really bad. That puts a burden on you, and it should put into question, what are we doing? Are our numbers valid or not? Now, this is not a new revelation. This was understood at the time that it was introduced. And so from the very beginning, it was recognized that business could not use binary floating point. So there were 2 schools of computation. On the scientific side, you had people writing Fortran using binary floating point. And on the business side, you had people writing COBOL using BCD, or binary coded decimal. Binary coded decimal uses 4 bits to represent a digit. So it's a little bit inefficient. You can try to figure out uses for the extra 6 codes, like it might be the decimal point, or it might be the minus sign, and you've still got more codes. But it worked. And the thing they liked about this was, instead of doing the divide by 10, they could do a shift by 4, which again is free. But it becomes a problem when COBOL goes extinct and Java becomes the successor to COBOL, but Java actually inherits from Fortran, and so its numbers are not the correct type of numbers for doing this kind of processing. And so that makes your jobs harder going forward, because your math is always in danger of not coming out right. Another problem with binary floating point is the difficulty of doing text conversion. Because there's not an exact one-to-one mapping between the binary values and the decimal values, there's some slop there. And so there are libraries that work very hard to try to make results that are correct, optimal, and unsurprising. And that turns out to be a difficult thing to do. It's a difficult thing to design, and it's computationally expensive. So most modern programming languages are a confusion of faulty number types. So if you look at Java, for example, every time you create a variable or a parameter or a property, you have to pick byte, short, jar, int, long float, or double, which one of those? And if you pick the right one, then your program's going to work. And if you pick the wrong one, your program's going to fail. But it's not going to fail right away, and it's probably going to pass all of the tests. But at some point in the future, eventually something's going to overflow and a terrible error is going to happen. And there is no benefit to going through this process. Because the reason we have all of these number types made sense in the 50s and made sense again a little bit in the 70s, that memory used to be really rare and really expensive. And so if your program was too big to fit into memory, it wouldn't run. And so you'd have to try to shave everything, make it as small as possible. That's not true anymore. Moore's law has been so incredibly generous on memory capacity. You don't understand how much memory you have now. Most of you have a gigabyte in your pocket right now. You don't understand how big a gigabyte is. So the idea of trying to save bits in a variable doesn't make sense anymore. It hasn't made sense for many decades. But we still do it. And in fact, our programming languages are demanding that we do it. And this can cause problems. For example, you probably remember the Ariane 5 disaster. It was a software error. That software was written in Ada, and I'm not going to show you the Ada, but this is the bug translated into Java. What happened was there was a value, a double value called horizontal bias, which was converted into a short. It overflowed. That was given to the control unit, which got confused, flipped the rocket over. It couldn't recover. They had to blow it up. That software error had an estimated cost of $500 million. Now, you probably haven't made an error yet in that magnitude, but it may be coming. So, we want to be careful with this stuff. So, but there is room for optimism. For example, JavaScript only has one number type, which avoids a large class of errors. You cannot make a mistake in JavaScript by choosing the wrong number type. And that, I think, is a really, really good thing. And it doesn't impair our ability to write good programs. We don't need all those types. We just need one that works. The only problem with JavaScript is it's the wrong type. And the reason it's the wrong type is because it is binary floating point. And what we really need is decimal floating point. Unfortunately, decimal floating point seems to have gone extinct. So I propose that we fix it. And this is my proposal, a new number type that I call DEX64, which I propose to be the only number type in well-designed application programming languages going forward. The only one. So in the language, it will not be called DEX64. It'll simply be called number, because that's what it is. It is the way you represent numbers in the language. If there's only one number type, you cannot make an error by choosing the wrong type. And that's a huge benefit. In hardware implementations, DEX64 integers can be added in a single cycle, eliminating the performance justification for int. So the nice thing about DEX64 is it does arithmetic the same way you did in school. Numbers work the way humans think about numbers. And elimination of numeric confusion reduces errors. So your intuitions about significance work in this one. You don't get the phantom significance that you get in binary floating point. Conversion of DEX64 numbers to text and back is simple, efficient, correct, and unsurprising, because there is a one-to-one mapping from the internal format to the external format. And it turns out it's trivial to do. It's the same as converting integers, which is trivial to do, adding the extra step of inserting the decimal point and possibly suppressing zeros on both sides. It's not difficult at all. So DEX64 can exactly represent decimal fractions with at least 16 digits of accuracy. That is the smallest number, smallest positive number that's not zero that we can represent, and that's the largest. And I think that's a sufficient range for most of the applications that we want to make in application languages. So this is what it looks like. It's a 64-bit word divided into two pieces. There's a 56-bit coefficient, which is just an integer, and an 8-bit exponent, which is just a smaller integer. And the value of the number is the coefficient times 10 raised to the exponent. So it's, the reason I made the exponent 8 is to make it easier for software implementations, because on Intel architecture, you can unpack that for free. You can take any existing int and turn it into one of these simply by shifting it 8 spaces. There's a reference implementation available on GitHub. So if anyone is designing a language and they'd like to do it right, you have an opportunity. If you'd like to read more about DEC64, you can go to dec64.com. So let's talk a little bit more about numbers. So 0 divided by 0, what is that? Any guesses? So it depends on who you talk to. So if you ask a mathematician, most mathematicians will say it's undefined. And they don't mean the silly way that JavaScript means undefined. They mean it doesn't make sense. You can't even talk about it. Shut up. It's meaningless. It's nonsense. You can't even do it. Except that we're not talking about mathematics. We're talking about computation. And if it's possible to do something, it will be done. So we have to decide what's the policy. What do we want to have happen? There's another school that says the machine should catch fire because nobody should ever do this. And so since no one will ever do it, it doesn't matter if it catches fire. And we know that's not true. There's one argument that says it should be null or some other NaN value. And that's reasonable. There's another argument that says, no, it really should be 0. The NaN thing is not important. And there's some places actually in business computation where 0 is the right answer. We sold 0 units this quarter, and total profit on those units was 0. So what was the average profit per unit? I think most business people would be really confused if that answer isn't 0 as well. So that's a well-formed thing. There's one argument that says it should be 1, right? Because n over n is 1, obviously, right? I once worked on a machine where the answer was 2. If you divide floating point 0 by floating point 0, the answer was exactly 2. This was on a machine designed by Seymour Cray, the best computer designer in history. And I can imagine there was a conversation at Control Data where somebody said, Seymour, there's a problem with divide. And he said, well, nobody's ever going to do that. And he said, well, maybe we should fix it anyway. And he said, look, divide is the slowest thing on the machine, and it's also the most expensive thing on the machine. And if I fix it, it's going to add another cycle to division, which is going to slow down everybody who's doing things correctly for the benefit of someone who's doing things wrong, and it doesn't matter anyway. So I'm not going to do it. So as far as I know, I'm the only person who ever divided 0 by 0 on that machine and got a 2. And it wasn't that big a problem, actually. So why do I care about that? I don't care about that case so much as I care about this one. What is 0 times n? Any guesses? So mathematicians will say, well, that's obviously 0. That's the only thing that makes sense. And for a long time, compiler writers who probably took a math class at some point, if during the compilation phase, if they find that there's a multiplication expression and one of the arguments is known at compile time to be a 0, and if the other thing has no side effects, if it's a pure expression, we don't have to do the multiplication. We can simply say that's a 0 too and be done. And so not only does the program get faster, but the compiler gets faster too. That's a really nice thing. Unfortunately, when the IEEE floating point standard was imposed, they said no. If n is NaN, then the result of this must be NaN, which meant that all of those compilers were in error and had to be repaired, had to be dumbed down, basically, in order to make this work. And I think this was a mistake. I think it should be 0. So why do I care? Who writes code like that? Well, not a lot of humans, but machines do. So code generators, macro processors, partial evaluators, they'll write code like this. And we can get better performance from them if 0 times n is 0. Also, non-conditional idioms benefit from this as well. One of the slowest things that happens on CPUs these days is conditional branches, because they're doing so much pipelining in order to try to get as much throughput through the machine. The pipelines get really long and really complex, and if there's ever a conditional jump then everything gets stalled until the conditional jump gets handled, and so it slows things down. So the benchmarks, if you ever look at them, tend not to have conditional jumps in them. They just want to compute a lot of stuff so they can get good numbers. But our programs tend to have conditional jumps in them. So there are idioms where you can use multiply times 0 and multiply times 1, and then add the terms together. Doing all of that extra work is faster than waiting for a condition to get evaluated. So that's another reason to do it. So that's why in DEC64, all of these forms will deliver 0 no matter what the value of n is, even if n is null or something nasty. So that brings me to the end. I have a few thank yous I need to do. Unfortunately, the people I want to thank are not here tonight because they're dead, but I feel I need to thank them anyway. So I want to start with Leonardo Fibonacci, who in the late 12th century visited Arabia and studied their advanced system of mathematics, learned their numbers and their algebra, their geometry, their algorithms, and brought that back to Europe, he published a book in 1202, which revealed to Europe the first time the brilliance of Arabian mathematics, with his own contributions, which advanced the state of accounting here, and also banking. He came up with formulas which enabled whole new kinds of banking to occur, which led to the generation of enormous amounts of capital which fueled the Renaissance. I want to thank Gottried Leibniz, the German mathematician, first for the calculus, that was great, but also for binary. He was the first guy to look at the Indian system and ask, well, what if this is base 2 instead of base 10? And he developed a system of arithmetic based on just 0 and 1, and he thought there was an amazing elegance and beauty in that, which of course there is. I want to thank George Boole, a British mathematician and logician. He developed a system of algebra based on the truth values, true and false. Brilliant stuff. We named Booleans after this guy. Alan Turing, another British mathematician, developed a model of computation with abstract machines. He found that one of the simplest possible machines was capable of computing anything that any other machine could compute. That was a really important step forward in the science of computation, so that the problem for later computer makers is basically one of optimization, because Turing already figured out the hard stuff. And then Claude Shannon, an American researcher, he did two amazing things. The first was he found a correspondence between Boole's Boolean algebra and circuit design, so that using Shannon's formula, you could convert Boolean logic into electronic logic, which is how we design everything. He also came up with a theory of information in which any analog signal could be converted into digital form and back to any degree of accuracy desired. And that enabled networking, and it enabled digital media. So all forms of graphics and sound, everything that we do, all of that wonderful, amazing, magical stuff happens as a direct consequence of Shannon. Then finally, I want to thank Tahuti. Unfortunately, I don't have a photograph of Tahuti. Tahuti invented writing. That's a big deal. He was the first scribe in Egypt. He was the one who discovered the rebus principle, which showed that if you have symbols that can be used to represent the sounds of things, you can put those together to form writing. He was the first guy to work that out. And coincidentally, he also created the job of scribe in Egypt, which turned out to be an important job because, well, in many religious traditions, it is written. So who wrote what was written? It turns out it was the scribes. And in Egypt, the scribes, when they were writing the myths of Egypt, they elevated Tahuti into a god. And Tahuti becomes the god of writing and magic. So why did they do that? They did it for two reasons. The first was they wanted to elevate the craft of writing. It's something so important that gods care about it because it made them more important, help them get paid and fed and all that stuff. The other was they wanted to thank Tahuti for having done that, for having given them the best jobs in Egypt. So today we know Tahuti as Thoth or Hermes, but he's the guy who started it. And in a very real sense, we are his children. So you are all the sons and daughters of Tahuti. Because what we do is we use writing to turn numbers into magic. Thank you.
Wow. Douglas, thank you very, very much. That was a profound talk. Thank you. Shall we take a few questions for Douglas before we wish him on? We wish that his work lives on for thousands of years like Tahuti's work. Any questions? Yes.
An historical, let's say, clarification, if I may. I think that B language had only one data type, and this was word. And then C language, introduced, byte, char and everything. So I guess it went from a bigger data type to a smaller one, from the 70s to the 80s.
Yeah, so the B language, which was a simplification of the BCPL language, was basically an untyped language. You just have words that contained bit patterns. And that turned out not to be enough, and that was the motivation for C, that you want to be able to distinguish addresses from numbers, from strings, from object references, and all of that other stuff. So you need types, but the confusion of integer types, for example, I think is counterproductive. It made sense for a while, like you remember the Atari 2600. That was the video computer system. It was the first computer in a lot of people's homes. That Atari sold millions and millions of them. It contained a 6507 processor with 128 bytes of RAM. 128 bytes, I said that correctly. And that included everything that you needed for running the program and the call stacks and everything. All of that fit in 128 bytes. So in that environment, you had to get really aggressive about trying to allocate as little memory as possible, or a few bits as possible to each variable. And the guys who programmed those machines were heroes. They really were. But it's not like that anymore. But our programming languages are still optimized for that case. And it doesn't make sense. We need to get past that. Thank you for the question.
So I would agree that they're heroes. I mean, if we look at the guidance computer that sent the Apollo mission up and the computing power that had versus the computing power we have in our pockets today, it's a whole different magnitude of things.
Yeah, so our computers today are at least 1 billion times better than they were just a few decades ago. But our software is not 1 billion times better.
Not at all. It's 1 billion times worse.
It's maybe on the order of 100 or 1,000 times better, but it's still way, we got an extra factor of 1 million we need to cover.
Any more remarks or questions for Douglas? How often will we have Douglas here? Come on. Don't be shy. Raise your hand. This is a great opportunity. Ne.
Douglas, do you think that can existing languages be fixed? Can this problem, the integer problem, be fixed with existing languages?
There's too much echo. I didn't quite make that up.
Do you believe that existing languages can be fixed?
Do I believe that existing languages can be fixed? No, I don't. I'm very much an advocate of making new ones. And we're in sort of a language renaissance right now, where there are lots of new languages being created, which I think is great. And I hope that experimentation continues and we find a good one. And I have spent some years trying to fix JavaScript and eventually determined that it's not possible. So.
I think we had another hand up there somewhere. Can you just raise your hand again so that I can come to you? There was someone. Oh, there you go. And here too? No?
What is your proposals for making a better software, except DEC 64?
I'm sorry.
What do you propose for making better software? How do we catch up to hardware?
What do you propose? What do you propose for making better software, and how do we catch up to making better software?
How do we make better software?
Yeah.
By writing better software. I mean, you know, our language, you know, it's often said that a craftsman blames his tools, and we can do that. None of our languages are perfect, none of our systems are perfect, but it's still possible to write good programs in bad languages. And so it's really on us to write good stuff. You know, for example, JavaScript, you can write really bad JavaScript, or you can write really good JavaScript, and it's really easy to tell one from the other. You know, ask JSLint, it'll tell you what the good stuff is and what the bad stuff is.
Yes.
So there are so many use cases that precise arithmetics has been like a demand in the last decades, from scientific computing to like financial analysis and everything. So how do those fields cope without having like a good, proper type system?
Again, I'm having trouble. Oh no,
So how do they benefit from having a strong type system? Is that correct? Is that what you asked?
Those scientific fields have practically fixed type systems so far. So how do they cope? User libraries or what?
how do they cope writing the scientific? It was just numbers. It's all numbers. And so, you know, Fortran provided integers and floating point, and that was enough to do their stuff. But yeah, it was enough. People were doing science in Fortran. People are still doing science in Fortran. Fortran is not dead yet.
The language that will never die. Hard to kill.
Well, I guess an obvious question. What was the motivation for coming up with JSON?
What was the motivation for coming up with JSON? It was desperation. So in 2000, I started a company to do Ajax. You all remember Ajax, right? It's what we do now, except we don't call it Ajax anymore. Our idea was that we can write applications that are delivered on a web page where if the user clicks on something, we don't have to pay the cost of a page replacement. We can simply send a little data there and a little data back and have JavaScript update the page. And we needed a format for getting the data back and forth. And we considered and immediately rejected XML because it was ridiculous. And we considered making up our own format, and I had this epiphany, well, the answer is already built into JavaScript. JavaScript's object literal notation is perfect for what we're doing, so we'll just adopt that, make a subset of it, and it goes back and forth. And it took off. Eventually. You know, it took 4 years to take off, which is pretty good. Usually a good idea takes at least a generation before it happens, because you have to wait for all the people who are invested in the old thing to retire or die before you can go ahead with the next one. the reason JSON was able to go so much faster was Ajax was discovered in 2005, and now people who had never used XML were starting to write web applications. And they were told at first, you have to use XML, and they said, well, this obviously is unacceptable. Or you could use JSON, and they all go, oh yeah, that makes so much more sense, and then it just took off.
One from me, if I may. In the last couple of days, I've been preparing for a talk around evolution. Do you believe, and often during whatever I've been searching, the element of threat and despair, which drives innovation, has come up a lot. Do you think that the majority of innovation comes through the sense of threat or the sense of despair versus the desire to improve?
No, I think we always have the desire to improve. The difficulty is that we don't improve fast enough. That our industry in particular has this idea that we're just waiting moment to moment for the next new idea, and then we all jump on it together and go forward. And that's not the way it happens. That something will be discovered, and we have to wait a generation, and then we'll jump on it. And we've seen this happen over and over again, and it's still happening. I'm a radical. I am not content to wait the generation. I want the new stuff now. And so I'm glad that we're in a period of innovation, and I'm hoping that somehow we can finally find the next good thing to get on and push it forward, that we won't have to wait another 20 years from the introduction of the next idea. You know, there's some brilliant stuff in Erlang, and they've just been kind of sitting out there being ignored by everybody. I think the thing that I love about Erlang, I think their contribution to us is the idea of a suicide pact. As far as I know, they're the first people to put that idea into a programming language, and it is so totally brilliant. I don't understand why all of the new languages don't have suicide pacts in them, because it's so smart. But you know, that was an idea that was discovered, how old are those guys now? Is it like 30 years ago? It's just a long time ago, and it still hasn't reached the mainstream yet. So the problem is, it's not that we're waiting for someone to have that idea, it's already happened. The problem is getting everybody to recognize that the good idea has already happened.
We have one more in the back over there. There's people, it's heating up. Awesome. Come.
So as the years pass by, we see more and more languages appear. Do you think this trend will keep like this, so we get more and more multiple languages, or will it at some point diverge to a single language that contains a lot of stuff?
Yeah, so I think we're following the pattern of evolution, where in evolution you see the tree of life will branch out and get bushy, and then there's a cataclysmic event, and it gets pared down to just one line. And we've seen this happen many times. You know, there was a book by Gene Sammet about programming languages that I think was published in the 60s, which has a picture of the Tower of Babel on the front with each of the bricks filled in with the name of a programming language. So even then it was perceived that there were a lot of languages, but there was Fortran and COBOL, and that was pretty much all that was actually being used at that time. You know, so there's lots of innovation, but only a few get major adoption in industry. And I think that pattern is always going to be with us. The difficulty is that once industry grabs hold of something, it's really hard to move it forward to the next thing. And so that's where I'm pushing and trying to get us to look at the next thing.
Yes, two more. Could you just pass it on, please?
First of all, thank you for your talk. It was pretty great. Thank you very much. You just said that we should develop new software and new languages. Who should develop those languages? Should it be the mathematicians, the businessmen, the computer programmers? Who should develop that new software?
I don't care. I think all of you should be building new programming languages. I think everybody should do it. Our most important tool is the programming language, and we all have the talent and the tools to make them ourselves. So I would like to see as much innovation happening here as possible. And then we have the problem of trying to figure out which is the one we should all conform to. But that's the next problem.
And we have one more, I think, over here. Here we go, Kostas. I'm going to touch the whole community today.
The question is, type systems for numbers aside, what other really big problems do we have in computing today and you would like to see solved as soon as possible?
I think our biggest problem is security. That because our programs are mediating everything that happens and we're writing in insecure programming languages and being sloppy in the way we compose the programs, we are exposing everybody to terrible harm all the time. So that's the first thing to fix. The second problem to fix is to do a better job of distribution. Almost all of our languages are optimized for the Fortran case, where we've got one program running in one CPU all by itself. And that made sense for a long time, but that's not how the world works anymore. We now have lots of cores, and we've got lots of machines and lots of clouds. It's all distributed everywhere. So the idea of having a program which is just one thing that runs in one place is a terribly archaic idea. That's not the way we should be thinking about it. We should be thinking about how do we distribute the computation to be going on everywhere. And we've made a little bit of progress with things like actors, but we still have a long way to go on that. So that's the other thing I'd like to see in the next language.
Okay, well, Douglas, thank you so much. Thank you for coming to Athens. Thank you for affecting the Athens ecosystem, the Athens software professionals, and thank you for inspiring them to go on and create, whether it's going to be a new language or a new number or a new anything. Can I ask our speakers, our esteemed speakers who have traveled so far and or have traveled from local, the best of Europe and the best of Greece and perhaps some further on from Europe, to please join Patroklos on the stage. Come on, guys, come on, let's get some activity going. I know it's Friday afternoon. I know some of you probably want to go to the beach. But as we stand under Tahuti and next to Douglas, come on, any more speakers? Let's come up, come on. Let's see if we can get a nice family photo, and one we can put on the wall next year. Where is Jessica? Where is who are we missing? Who are we missing?
We are missing some. Maybe they are left.
Are they in the bar? Are they drinking? Okay. A huge applause to our speakers who traveled so far. As we say in Greek, who gave us their light. Thank you for giving us your light. Thank you for giving us your knowledge. Thank you for sharing. Thank you for being here. Thank you for taking the time. It's been a truly valuable experience for everybody. I hope we can welcome you back perhaps next year or another year for a contribution. Or just a drink. And before I ask our speakers to step off the stage, can I ask all of the team, the volunteers and the staff, to please come up on the stage so we can thank you for all the effort of putting this together. Come up. Come up. Anybody left in the... No? The whole Voxxed Days Athens team. What a fantastic event this has been. I think we were missing one big developer event or developer conference in Athens, and I think it's finally arrived. I'm really, really glad that this is here now, and we can say a big thank you to Patroklo. Patroklo, take the microphone. I want you to say what you got to say.
A big thank you, guys. Thanks to all the speakers who joined and accepted my invitation, to the volunteers, of course to you. It was an amazing event. I enjoyed it. I hope that you did enjoy it as much as I did. I'm relaxed right now. So see you next year again, probably, or in 6 months in Thessaloniki, if you want to have a nice weekend. And it's time for beers, okay? Cabrio Bar, see you all there. Thank you guys, bye-bye.
Can we take like this first row just a little lower down? Not too much, just opposite me. You okay?